Your instance methods work perfectly in Python, but the moment you try to expose them to an LLM through FastMCP, everything breaks because of that self parameter. Here's how to properly register bound methods so your tools work seamlessly, without confusing the AI or breaking your existing code. You'll see the exact pattern to create an instance first, then register its methods, making them callable without exposing self to the LLM. From FastMCP, import FastMCP. MCP equals FastMCP. Class myClass. Def add self x y. Return x plus y. Hash create an instance first, then register the bound methods. Obj equals myClass. MCP tool obj add. Hash now you can call it without self, showing up as a parameter. Await MCP. MCP call tool add x 1 y 2. Hash returns 3. This demonstrates the bound method registration pattern, a technique for exposing object-oriented methods as standalone callable tools without framework coupling. The key insight is treating method registration as a separate step from class definition, which preserves Python's native method binding behavior while making methods available to external systems. Unlike traditional decorators that transform methods at definition time, this approach registers already bound methods, avoiding the self-parameter exposure problem entirely. The pattern works by leveraging Python's method binding system rather than fighting it. When you register obj method, instead of decorating method directly, you capture a callable where the instance context is already resolved, exposing only the intended parameters to callers. This maintains clean separation between your class's internal structure and its external interface, with the registration step acting as an explicit bridge between object-oriented design and procedural tool exposure. This approach solves the fundamental tension between encapsulation and tool exposure in AI automation systems. It lets you organize related functionality in classes while still making individual methods callable as discrete tools, without leaking implementation details like self or CLS parameters. The trade-off is slightly more verbose registration, but the benefit is proper method binding and cleaner architectural boundaries between your domain logic and the tooling layer. Let's break it down. From FastMCP, import FastMCP. This imports FastMCP, the core class for creating AI-callable tools. It bridges Python functions to AI models, enabling direct execution of your code from AI workflows. MCP equals FastMCP. Instantiates the FastMCP server, the central orchestrator for AI tool execution. This single instance manages all registered tools, handles serialization, and routes calls between Python and AI models, required before registering any tools. Class myClass. Def add self x y. Return x plus y. This defines a simple class with an instance method that performs basic arithmetic. The add method takes self, x, and y parameters, implementing the standard Python instance method pattern where self binds to the object instance. This becomes important later when we register the bound method as an AI-callable tool. Hash create an instance first, then register the bound methods. Obj equals myClass. MCP tool obj add. This instantiates myClass and registers its bound method as an AI-callable tool. By passing objadd instead of myClassAdd, we bind the method to the instance, eliminating the need to manually pass self during AI invocation. This pattern ensures the tool maintains proper instance state when called remotely. Hash now you can call it without self, showing up as a parameter. Await MCP. MCP call tool add x 1 y 2. Hash returns 3. This demonstrates FastMCP's bound method invocation pattern. The MCP call tool handles the instance binding automatically, eliminating the need to expose self in the tool's interface. You pass only the method's actual parameters as a dictionary, keeping the API clean for AI consumption. Bound method registration pattern. The instance-first approach to tool registration eliminates the self parameter from the LLM's perspective by binding the method to its object before exposure. Failing to register bound methods will expose self as a required parameter, causing runtime errors when the LLM can't provide it. This pattern maintains clean separation between class implementation and AI interface, without sacrificing Python's object-oriented features.
The method that forgets its owner becomes universally callable.